responses to go over on units 3 and 4. Lots of great information that hopefully will help you prepare for the AP exam coming up on Thursday, May 14th at 1 p.m. Just a few announcements before we get started. For teachers, the free response questions that A+ College Ready has in Canvas might be really helpful for you, since those are topic specific. I know a lot of the AP Classroom free response are great, but we had narrowed down the free response to deal with certain topics. So you might consider using that with your students. Also, teachers had a webinar this is for information for students and teachers, a couple of nights ago with the College Board. It was very informative. There's been talk about everyone needing a lockdown browser on their computer to take the exam. That is not necessary. That would cause way too many problems. So no lockdown browsers needed. No one on any science test will be asked to draw a graph, but we will be asked to, or you will be asked to analyze graphs and, you know, other diagrams and things. So that should be helpful. The test, as I mentioned in the webinar, the exam is designed to be used so that you can type your answers in. You do not have to do that. You're also welcome to handwrite your answers and upload photos. So we will be receiving, you will, students and teachers, we all will be receiving very detailed information starting the week of April 27th. You will be given a test taking guide. And so teachers will have that PowerPoint to roll out to students, and students, you also will receive that information. So just wanted to keep you updated. Always check the College Board website for the information you need. Make sure, students, that your current email is updated in your AP account, because that's how you will receive information. And then you're also going to end up getting an e-ticket to use the day of the test. So all that information's coming soon. If you have a question, you're welcome at any time to type it into the chat box, or if you'll keep your microphones muted so we don't have a bunch of background noise, you can also just see if we have any questions. Yeah, there's the test day webinar for teachers. Thanks, Matt. Yes, I make sure teachers, you've signed up for that. Okay, so just keep yourself muted unless you want to ask a question verbally, or you're welcome to type it in, whatever you feel more comfortable doing. I would love for you to ask questions. It makes it a much more valuable time if you can ask questions as we go, or if something doesn't quite make sense to you. So for right now, I'm going to, because it's distracting to have someone looking into the computer at you, I'm going to take down my video, but you'll still hear my voice, and I'm going to put up the free response questions. So if you could find a calculator, you know, some paper. If you have the free response questions printed, that's great. If not, they will be displayed as we go through them. Periodic table would be great, if I didn't say that, and formula sheet. Okay, so let's go ahead and get started. Let me switch to the other screen. All right, so we'll just jump right in. This first question is really a review from the last unit, but as you know, on an AP exam, all the free response will include lots of different information put together. So just quickly, we can run through A just to answer the question. Notice we have this compound urea. It's used in chemical fertilizers. Complete the Lewis diagram dot structure shown below. All right, number 1A, identify the hybridization of the valence orbitals in the carbon compound. What I did not give you here, and this was given above, is it told you this complete structure was actually given above, and so you were asked to do the hybridization. If you go back and look at the worksheet, you will see that it is given there, and it's sp2. Okay, so I'll go ahead and give you that answer. sp2. All right. It's harder to see it in this box drawing below. So let me scroll down a little bit and let's look at part B, because this is really where Unit 3 is going to start. I just, hold on just one moment. On my screen, I lost a, okay. All right, so I'm going to scroll down a little bit. All right, so urea, it says, has a high solubility in water, due in part to its ability to form hydrogen bonds. Wow, what a great piece of information they're giving us. They're telling us the exact IMF, which is definitely a huge part of Unit 3. Just to review IMFs really quickly, we need a hydrogen on one molecule that is attracted, this is our dotted line, our hydrogen bond, to a fluorine, oxygen, or nitrogen on an adjacent molecule, but that hydrogen itself has to be covalently bonded to one of those three really electronegative elements as well. Okay, so just want to review that. So what we're asked here is to draw one dashed line, just one, to indicate a possible location of a hydrogen bond between a water molecule and the urea molecule. Okay, there's lots of options here. I think when I first looked at this, the first place I came up with one is between this right here, between those two. And again, this is, okay, so there we go, there's one. Another place you might have seen is, because if we notice you know, this was oxygen and there's my hydrogen. But here, this would be the same thing if I do it right here. I'm having a hard time doing a dotted line here. Of course, one thing I don't want to do is, and this is what unfortunately some students did on this exam, is they did that, and that would be a mistake. That's a big X. I could do one here, and again, there are many answers for that question, which is nice when there's just not just one correct answer for a question. All right, so let's keep going for the next part of this. Again, here's just the next part of the question, just to show it on the screen. The dissolution of urea is represented by the equation above, and that was actually on the bottom of that screen. Let me go ahead and just show you where that was. This would, of course, would have all been stacked together. And it's right under this drawing, and under that box. Okay. So that's a dissolution. Notice it's just the dissolving in water. Okay, just want to make sure there are no questions about the wording here. Okay, so we have a student determines that 5.39 grams of the urea, and there's its molar mass, so that's a hugely helpful piece of information because we might need to use that. Can dissolve in water to make 5 milliliters of a saturated solution at 20 degrees Celsius. So our part C is calculate the concentration of urea in moles per liter in the saturated solution. All right, if we go to our formula sheet, if you'll flip over to the back, I have some excerpts later on in the presentation, but it says in words under that gas, liquid, solution area, it says molarity equals moles of solute per liter of solution. So this should be a math question that we can easily get. So we have our mass right here, 5.39 grams. Just think in your head, start writing it down. What would you do to solve this? We would take our 5.39 grams, we would divide it by our molar mass to get moles, and then how do we get molarity? Well, it's moles per liter. The problem is I have milliliters. So we have, that's where a common mistake would be, is for students to not change milliliters to liters. So again, think milliliters to liters, you're going to have to divide by 1,000. All right, so I'm sure you're all thinking that. So I'm going to reveal the rubric that was on that exam. Notice, you know, they've shown all this work, as long as you're showing that you're dividing, 5.39 divided by 60.06. Some people might have done this in one math step. That is fine. Notice that the moles, that first point, can be implicit. Some people would set this up as one long math problem. The key, though, is you have to change the milliliters to liters. So don't forget that. You know, since this is an exam where it's open note, these are things, these little details that we shouldn't miss. Okay, let's move on to the next part. And on this one, looks like I make that. All right, so it kind of got a little covered up with my, there, that looks better. Okay, so a student is given 50 milliliters, and this is a different question. This is free response number 2. Okay, just taking excerpts of different ones. It's given a 50 milliliter solution of sodium carbonate of unknown concentration. To determine the concentration of the solution, the student mixes the solution with excess, and again, I'm going to underline that because it may or may not be important. It just depends on the question, causing a precipitate to form. So we see this solid here. There's our precipitate. There's our balanced equation. A, write the net ionic equation for the reaction that occurs when the solutions are mixed. I don't think there's a question that you're going to have to write some kind of reaction on this test. It could be this, maybe this kind of precipitation. It might be acid-base. We'll talk about that later, or redox. But let's just kind of go over the basics here. When you see AQ, I would circle those. Anything in this reaction that's AQ, unless it's a weak acid, which we'll talk about later, we're going to split it up into ions, or a weak base. Okay, so splitting this up, I'm just going to go through this one pretty specific, what I would be thinking to get my answer. Okay, I've got 2 sodium ions. Looks like it's not showing there, it's on your screen. And then, see, in this one, it's dissolved, it's not together like this formula, this ionic formula implies. It's actually completely separate ions. And then I've got my calcium ion. Notice I'm not writing states. And if there's subscripts, like the 2 outside my parentheses, remember it would become a coefficient, just like with the sodium at the beginning. So really, those 2 solutions are completely separate ions because they're both dissolved. And that's what ionic compounds really look like when they're dissolved. And then my product, I'm going to distribute my coefficient of a 2. And again, this isn't my answer. Okay, I'm going to have a lot more room on, I have as much room as I want when I'm writing my answer. And then my product is my precipitate, calcium carbonate. And that's the one thing I'm not going to split up, because that's the precipitate. That is, we'll scroll down in a minute and you'll see that is the solid at the bottom of the beaker. Okay, so what's my net ionic? Well, it's everything that's not staying dissolved. So I'm going to mark out my spectator ions, the different ions that are staying dissolved, and whatever I have left, you can circle it if you want. I would not want to leave it like this on the AP exam. I would want to write my own answer, rewrite it, and only include the ions that are making the precipitate. Now, things that happen, unfortunately, that cause students not to get credit is they forgot to write a charge on an ion. Maybe, this one works out, well, it's very lovely that we don't have to actually add any coefficients to balance the net ionic. It is balanced as it is. That could be an issue. Just be really careful. Like, once you write your final answer, look at it. Does every element balance on both sides of the reaction, and do the charges balance? Because notice my reactants, total charge -2 plus +2 is 0, and my product has no overall charge. That means it's balanced for elements, and now it is also, I can confirm, balanced for charge. And that, this is only going to be worth 1 point, so you don't want to miss that 1 point. Okay, let me scroll down. Okay, so that would be my answer that I wrote next to the beaker. All right, so moving to the next question. The diagram below is incomplete. Let me give us some more room. There. Draw in the species needed to accurately represent the major ionic species remaining in the solution after the reaction has been completed. Okay, so this is our product beaker. The reaction's taking place. We see our solid at the bottom. The easiest thing to do for something like this is to add up the charges that are already in the drawing. This is where I would tell you to start. okay? So I've noticed there are two positives. I've got a sodium. I'm just going to put checks on them, then know I've counted them. So I've got +2 for the sodiums. And then for nitrates, there's 1, 2, 3, 4. So I've got -4. Well, see, this is what we have to think about. If my reaction has to be balanced, my beaker charges actually have to be balanced too. So you can see I have 2 more negatives than I have positives. So there's some positive charge, and it's got to be a +2 because, again, these both have to, when I add these together, it has to equal 0. So what's missing? Well, if I scroll back up, you might have already figured out what's missing. If I scroll back up, what was in excess? Because it's something that's in excess that's missing. Notice I had a lot of nitrate, ion in the solution. So what else should be in excess? Well, it's our calcium. So that's what they expected you to draw in this question. Just 1 calcium ion. And why just 1? Because that's that +2 charge that's missing that would make that reaction container balanced for charge. Okay, that was a really good question. I could see, could they ask this year? I don't think, if you might have to type into a drawing like this. I don't think they could ask you. I don't think so. But couldn't you just write an answer to that without having to draw it in the beaker? Couldn't you just say the beaker's missing 1 calcium ion? That's just another way this could be asked. So moving on to the next part of this question. Okay, we're in the same free response. The student filters and dries the precipitate of calcium carbonate. And there's a molar mass again, and it's so nice when they give us the molar mass. And I don't feel like that's going to be anything. I think that will continue on this exam, that they're going to continue to give us molar masses to speed up our math and hopefully give us clues if we need it. Okay, so let's see if we need that. Sometimes you do, sometimes you don't. The student filters and dries the precipitate and records the data in the table below. Okay, determine, and we've got some information. We've got volumes, a mass of the precipitate. Determine the number of moles of sodium carbonate in the original 50 milliliter solution. Well, if we go back to our reaction, our reaction involved this sodium carbonate and this calcium nitrate. Okay, so we're supposed to figure out how much, answer the question based on sodium carbonate. So determine the number of moles of sodium carbonate in the original 50 milliliter solution. Okay, well, we don't, if we had a molarity, then we could, easily figure it out. All we have about it is its volume. We don't have enough information to figure out moles from that. So what we're going to have to do, and this is a very common question when you're doing stoichiometry, is to be given a mass of a precipitate, like this is a lab, for given a mass of a precipitate, and be asked to answer a question about something about the reactants. Okay, so just keep that in mind. That's very, very common. So what should we do? Well, if we have grams of a precipitate, our first step should be to change those to moles. Very, very common. You're going to definitely be doing some of this. So grams to moles. But if you notice, that's calcium carbonate. This is another place students make mistake. They do change grams to moles, but then that's not the answer. I need sodium carbonate. So to get sodium carbonate, I've got to do a mole to mole ratio. So if I go back to my reaction, oh, wow, it is 1 to 1. Okay, do I need to write that? Definitely. Okay, so let's scroll down and see how you would set this up. But think in your mind, you've got to change grams to moles. We were given the molar mass. Okay, so there's that. That's that calculation. And then you're expected to realize, hey, even though this is a 1 to 1 mole ratio, I have to represent that in writing. Okay, so again, just remember there's a lot of lab type, it's called gravimetric analysis questions, where you're given information about a precipitate and asked questions about a reactant. So that's very commonly something you might have to solve for. Okay, let's keep going with this free response. Part D, and there's the answer. Sorry, wasn't supposed to be covered. All right. Let me see if I can fix that. My little revealer tool is, anyway, I think you've already seen it, so I think it's kind of it was all covered before. All right, so it says the precipitate was not completely dried and claims that as a result, the calculated molarity of the sodium carbonate is too low. Okay, now let's think about this. If we're saying, and let's just go back since that we already have the answer. If we're saying that the precipitate collected was not completely dry, that means some of this mass actually had water with it. Okay, so if some of the mass that we measured is overinflated, right? Okay, so let's go back and think about this. The student's claiming that the molarity would be too low. Well, that should not make sense, because if the mass is overinflated, that means the moles are overinflated. So 1-to-1 mole ratio, that means we'd have way too many moles than were actually there. So the molarity would be too high. So they were looking for you to say disagree, okay? And again, you can say it in your own words. I know the rubrics always sound perfect, but you know, you just have to, the important thing here to get this point is to walk through very specifically how all of your values are affected, okay? So I'll just read the rubric, but again, I use the term mass was overinflated. There are lots of ways you can say this, okay? So the presence of water caused the measured mass to be greater than it really was, or than it actually was, okay? So do you see how you can change it and put it in your own words? So that would cause the moles to be too overinflated or be too great, and therefore the moles of both. You have to really, what they were looking for here, I actually graded this question last year. They were looking for you to say mass was too great, which caused these moles of calcium carbonate and sodium carbonate to be too great, so the concentration is too high. Okay, that's kind of a lot to get a point, but the problem is a lot of times students, when they give you one of these lab error questions, they just don't specifically walk through what the problem was. Okay, so just remember that, and this is a good thing to practice, because a lot of these lab questions have some kind of error analysis, and you really need to practice, you know, walking through, okay, how would this problem affect this number? Look at your calculations, and what would that cause, you know, the calculation to be off. You can't just say the calculation is off. That would never, it's either got to be too high or too low. You got to specifically walk through, you know, what that is going to affect. Okay, and all my revealers are gone. That is not good. Okay, sorry guys, I had all this. I don't know what happened. Okay, after the precipitate forms and is filtered, the liquid that passed through the filter is tested to see if it can conduct electricity. Okay, another word for this liquid, which students really should know, but they're not going to use, you know, they didn't use it, is called the filtrate. The liquid that goes through the filter paper is called the filtrate. Okay, so they're asking a very specific quality about the liquid that went through the filter paper. Will it conduct electricity? So what do we think? So we're talking about, and what's the purpose of using the filter paper? We're trying to filter out the precipitate. So if we go back to our original container, this is what it looked like. You know, this was our original container in our picture that we drew in a calcium ion. If we got it right or not, this is what was in the solution. So will this solution conduct electricity? And the answer is Yes, you should say yes, because any solution that has the presence of ions in it is a conductor of electricity. And that's what they wanted you to mention there. And there are my revealers now. Isn't that interesting? Okay, so the answer is yes, it will. And you needed to say there are ions present in the solution. Okay, now you should have known there are sodium ions and nitrate ions. You know, if you mention an ion that wasn't present, you did not get credit unless you had actually drawn. Anyway, just look at the picture and say there were the presence of ions. And again, saying sodium ion and nitrate ion, and hopefully calcium, if you got that right, would be extremely make your answer more specific and even better. Okay, let me see if going back, I'm sorry for the problem. I had a revealer on each slide. Let me go ahead and add it here, and then hopefully I won't have the problem for the rest of the PowerPoint. Okay, here we go. Now we're on free response number 3, and it says a student investigates the reaction between, that's hydrogen peroxide and sodium hypochlorite, which is represented by the net ionic equation above. So they gave us a net ionic equation, so that's great, but they're going to ask us about it. So A, is this reaction represented above a redox reaction? And so again, it says justify our answer. So think about what does redox mean? We've got 2 parts of it. Something has to be oxidized and something has to be reduced. So I don't know if you remembered Leo the lion says grr, or maybe you remembered oil rig, either one, but oxidation involves loss of electrons, reduction involves gain of electrons, but the easiest thing to see is reduction means the oxidation number will be reduced. So if we go through this and write our oxidation numbers, we can see if we have to have something to be oxidized and something to be reduced. And if that is the case, then we know that we have this reaction. We can answer the question. So hopefully you know that hydrogen is, when it's bonded to a nonmetal in a compound, is going to have an oxidation number of +1. And then oxygen typically is -2 as its normal like ionic charge we think of. But when we see peroxide, this is the one time that you have to remember that it's -1. And that could come up with oxidation reduction. Now when we get to this hypochlorite ion, again, oxygen in polyatomic ions is going to be -2 like you'd normally expect. Now this is where chlorine is kind of a weird charge this time, because remember when we add the oxidation numbers together for parts of an ion, so I'm leaving a blank here for what the chlorine oxidation number would be. These two together have to equal whatever the overall charge of that ion is. Okay, so I've got +2. Chlorine had to be something to get -1 overall. Well, it seems really strange, but it is correct that chlorine would have to be +1. Okay, remember oxidation numbers aren't, so don't just assume chlorine's going to be -1 since it's a halogen. That's its ionic charge, but we're talking about oxidation numbers. Okay, hydrogen and water is 1. Here's where we see oxygen and its normal oxidation number of -2. If we have a monatomic ion, just a 1 atom ion, it's going to be its charge. And so you notice we're getting some variations. And then O2 is a diatomic element, and elements are 0. So if I look at this, is this a redox reaction? Well, there's no question it is. So I would say, yes, this is redox. How do I know? Well, I've got 2 different things changing oxidation numbers. So I've got oxygen going from -1 to 0. I've got oxygen going -2 to 0. And then there's there are a bunch of charges for oxygen. So there's no question oxygen's involved. And then I also know that chlorine is involved. So in this case, since it didn't specifically ask us to mention oxidation numbers, they did give credit for all you had to say was that yes, it is redox because chlorine and oxygen underwent changes in their oxidation number. Now, this is a complicated one. If they wanted you to say specifically what was going through a change in oxidation number, and we'll see that later on, we're asked about a different reaction, and it ends up being manganese. But here, you can tell that chlorine, and I don't want to spend way too much time on this, but I do think there's going to be something about oxidation numbers or redox on this exam. I'm just guessing. I wish I had inside information, but I do not. If you see chlorine right here is going from +1 in the hypochlorite ion to -1 as chloride, the only thing chlorine can be doing here is being reduced. Okay, and I'm trying to type with my keyboard, so it looks pretty bad. So you know that chlorine is reduced. So that means oxygen, and I'd have to come up with some example as oxygen being oxidized, because it would have to go up in charge. So there's really, I did this earlier, there's really two choices. Either oxygen is going from -1 to 0, or oxygen's going from -2, and I'm not going to try to draw that again, -2 to 0. Okay, why do I know it couldn't be -1, I mean -2 to, excuse me, -1 to -2, because there can't be two reductions. So oxygen had to be oxidized. Okay, if you have any questions about that, I'll be happy to answer them. And I can give my email too if anybody wants to ask me anything later. Okay, the next question here. We'll go to the next slide. And this just shows how they mix a lot of things together. Okay, there's really not a question on this slide. This was in the next part of the question. It gives you a lot of information at the beginning. Okay, you can see that this is actually a redox titration. And since one of the products is a gas, they're collecting this gas over water. It looks really complicated, but you might have done a redox titration, possibly. It doesn't really matter if you've done one or not. You know this hopefully is a burette, that's a flask. They're trying to get whatever amount of this solution that's in this flask, they're going to add just enough of this other reactant so they exactly react. Okay, or maybe you've just done collecting a gas over water reaction, and it, you know, this is kind of unusual for it to include both. My students would have never done this. It's way too complicated, but we can put everything we know about these two things together. And really the questions that come after this really aren't that difficult. So what I'm encouraging you to do is when you see something like this that looks complicated, read what it says. Notice there's a volume of oxygen gas, there's a pressure, a temperature. It's talking about a reaction, and it says that this gas collection tube was initially filled with water. Okay, so notice as the reaction goes on, the oxygen gas bubbles up and displaces the water. Okay, so just wanted you to see that apparatus. Look at the next question though. It's really not that bad, and I just totally, I don't know what I did. All right, give me just a second. For some reason, I guess I closed the flip chart. Sorry. Okay, let me get back to where we were. All right, so the next, this was the question after that diagram. Calculate the volume, and I would circle that, highlight it, you know, just realize I need a volume for my answer of a 0.800 molar solution of, here's our hydrogen peroxide, that the student should add to excess sodium hypochlorite to produce, and here's the same numbers they gave us previously, 40 milliliters of oxygen gas at 0.988 atmospheres and 298 Kelvin. Okay, when you see that this information is about a gas, I hope that kind of really jogs a memory for you. So looking at this information, if it's a gas and we have all this, what would we use to solve that? Hopefully you're thinking PV equals nRT? And if you did, you are correct. Now, is that all we have to do? Well, probably not, but as a good start, we need to think, okay, a bunch of stuff's going on. I've got this reaction, it's producing a gas. Again, if you have a reaction producing a gas, you know, typically on the traditional exams, you've always had to solve for PV equals nRT once. If you look at your formula sheet, the pressure unit is what tells us which R to use. Okay, so if you look at your formula sheet, you'll see that we need to use the 0.08206 version. It has atmospheres in it. Look at the units for R, and you can tell what all of our other units need to be. So R is in atmospheres. We have a temperature. It's already in Kelvin, and that is a good thing. That's what we need. Here's our problem, though. This is not going to work. Okay, we cannot use milliliters. So hopefully you have thought of that you have got to, let me look at one thing, that you've got to change milliliters to liters. So let's go ahead and do that. So we've got point divided by 1,000, I'll have 0.0400 liters. Okay, plug in. What are we solving for PV equals nRT? Well, we're not solving for volume because that's the initial question, but we've got to, as you'll see, we need an intermediate answer before we can get to that. So we're looking at our PV. We have pressure and atmospheres. We're changing our volume to liters. It's in. We need moles from PV equals nRT. Our R is our constant we looked up. Sorry, I'm trying to type. My stylus isn't working. And let's reveal and see that set up. Go ahead and calculate that. We're going to do one more calculation a little bit later. I just wanted you to think through it. Okay, so once we have moles of oxygen, this is going to be a 2-point question. You're going to get 1 point for that. That does not answer the question. The question is calculate the volume of a 0.800 molar solution of hydrogen peroxide. Well, I need to go back to my reaction. What is the relationship between oxygen gas and hydrogen peroxide? Because I know moles of oxygen gas. So let me see. Oh, wow. Aren't we lucky? It's 1-to-1 again. So do I need to show that? As we saw earlier, yes. So I'm going to take my moles of oxygen. Okay, take my moles of oxygen, convert those to moles of hydrogen peroxide, and then plug into my molarity relationship. Now, people set this up differently, but basically another way to set this up would be, and you know, students, you do what makes sense to you. Some of my students would write 0.800 equals, sorry, I wish my stylus would work. And then I've got my moles I would put as my numerator, and I'd be solving for my volume as my denominator. So I would just put this answer right there. Okay, so 0.800 equals that many moles divided by the unknown volume. Do my algebra and solve. They've just used their molarity as a conversion factor. Okay, so if that looks a little different, it's the same math. And we do need, you could answer in liters. If you changed it to milliliters, you could do that. It has not asked for a specific volume unit. I would not do extra math to change units unless you were asked for that, because if your final answer, if you did a unit conversion incorrectly, you would not get credit for that final answer. Okay, so 1 point for solving PV equals nRT, and then 1 point for doing that mole to mole ratio and calculating the volume from the molarity. Okay, the next part, let me go backwards one more time. All right, going to the next screen. There, back to where it was. Okay, so now we've got a, this tells us this is the gas collecting tube. And as on several exams, there's been a piece of lab equipment that you had to interpret the measurement from that. And so I do think this is a good thing to just quickly go over, because unfortunately this should be an easy point. A lot of people miss it, okay? So it just says, based on the diagram above, what volume of gas was collected? Okay, so when you're doing a question like this is going to be significant figures. If you have not enough or too many, you're not going to get any credit. So notice this volume is between 30 and 40, okay? Now notice it's going down, like 0 was at the top, okay? So this answer is going to be 30 something, right? Okay, so it's going to be 30 something. Now, how many decimal places do I need? Do I need 1 or 2? Well, it's easy to figure out. Look at the lines that don't have markings. Notice they must be 1 milliliter each, okay? So if my volume is between the lines, I would need 1 more decimal place to correctly report the volume. So that tells me I need to, figure out exactly what this is. Look at the bottom of the meniscus, and it would be, that's 35 right here. So it's below 36. And then you're going to estimate this digit. If, you could say it's 36.4, 36.3. The key actually says 36.5. If you're somewhere close to that, between 36 and 37, you're going to get credit for that. So again, see what that next digit, those unmarked markings are. Oh my goodness. All right. The last question here is a percent yield question. Let me scroll down. Okay. It says that the tube should have, the reaction should have produced 40 milliliters. And it's asking you what's the percent yield. Well, whatever answer you got in your previous question is your actual. So remember, your actual lab information is the actual, and you will be told something that would have been, see, it should have produced 40 milliliters. Okay, so if we go to our percent yield, and again, this isn't on the formula sheet, but you can make your own formula sheet now because it's open note. Percent yield is actual over theoretical times 100. If you go down, look at this next. So it's a very simple calculation, 36.5 or whatever. Again, if you had 36.4, whatever volume you had answered for the previous question would have been your answer. Okay, moving on to the next one. Now we're going to get to another IMF question. This was an older one. I think it's still a very good question, and I can see something like this. They like to give you structure, especially, I don't know if you're going to have to try to draw a load structure on this exam. I would think not if they expect you to type, but I can't promise anything like that. But again, it says you've got 2 structures. We've got glucose and cyclohexane. Identify the types, plural, so that means there could be more than one in each of these. So when I look at glucose, these OH groups, they're called hydroxyl groups. You don't have to know that name. When you see those should jump out at you, okay? Any carbon compound with the presence of those OH groups, those are sites of hydrogen bonding, okay? Just think of this like part of a water molecule. All right, so what are our answers for glucose? Definitely hydrogen bonding. Okay, and any polar molecule also, they're expecting you to have 2 answers here, would also be London dispersion forces. So make sure you would have 2 answers there. And then if you look at cyclohexane, it doesn't have any very electronegative elements, and it's completely symmetrical, so therefore it's only going to have LDS. So that's going to be my only answer there. Okay, going on to the next part, it says glucose is soluble in water, but cyclohexane is not. Okay, so how do we explain that? Well, what they're looking for here is a very specific relationship between each molecule in water. Okay, so you need to mention both structures in your answer and say that structure's ability to be attracted to water. So is glucose attracted to water? Well, definitely, because they just told us it was soluble. So glucose is soluble in water due to the fact it can hydrogen bond with water. Okay, that gets to the point. That's enough information. Glucose, and you could write being polar, that would be nice. Not required. Glucose is soluble in water because it would be able to hydrogen bond in water, or has a great attraction with water through hydrogen bonding. All right. Cyclohexane, due to it being nonpolar, would only be able to have weaker London dispersion forces of attraction with water, which aren't strong enough to make it soluble. Okay, so you need very specific, very specific answers there. Please don't say like dissolve like. That's not enough for AP chemistry. I think that's a great way to think about it. Polar things dissolve in polar water. You need to be more specific than that. Okay. Let's go to the next slide. And here is the specific rubric if you want to read through that answer. I really like the next part of this question. It gives you two processes, and it says, for each of these two, identify the types of intermolecular forces or intramolecular attractive forces that must be overcome. All right, intermolecular, remember that's what we call IMFs, which could be hydrogen bonding, London dispersion, dipole-dipole. Intramolecular are bonds, okay? So covalent, ionic, things like that. So in this first process, notice water is still water. That is, and if you look, it's liquid to gas. That's what we call vaporizing or boiling. That is a physical change, okay? Physical changes with molecular compounds are where we have what we call intermolecular forces. So we've got to talk about what's been broken up between the water molecules. Keyword with IMFs is between, okay? So this is a physical change. Now look at process 2, that's an actual reaction. That's a chemical change. You can tell that water molecule has been internally broken apart. So this is how we're going to answer this. So for process 1, we would say hydrogen bonds are broken, hydrogen bonding between the water molecules. You could also mention LDFs, hydrogen bonding is going to be the key. And then for process 2, hopefully you would say covalent bonds. And when I gave this on a test, my students for process 2 said covalent bonds, and then they listed the IMFs as well. Not necessary. All that you need to mention for process 2 are covalent bonds. Mentioning everything sounds like you don't know what you're talking about and you're just writing everything you can think of. They're only looking for you to write an answer there that is intramolecular answer, covalent bonds for process 2. Okay, moving to the next part of this. Love this. I use this a lot in my class. Indicate whether you agree or disagree with the statement in the box below. Support your answer with a short explanation. When water boils, water molecules break apart to form hydrogen molecules and oxygen molecules. So if we go back to the previous slide, what does the box explain? Well, the box is explaining process 2. Is that what happens when I boil water? Of course not. Okay, so look at the information above, because this again would have all been stacked together, and hopefully you would think, oh, I'm going to disagree with that, but how am I going to explain it? Well, boiling involves the breaking of hydrogen bonds. You could just kind of go back to what you said before, or just intermolecular forces between water. No bonds are broken. No covalent bonds are broken. Okay, I think that's a great question. All right, we're going to get to the next one, and it's a little bit more with IMFs, because IMFs, I definitely think you're going to see a question when you know, an IMF question on this test, but again, we'll wait and see. Got to be ready though. Okay, so this is interesting. The AP exam likes to give you data, and you have to explain the data. Okay, so boiling point of bromine is 332. Whereas the boiling point of BRCl is 278. Explain this difference in boiling point in terms of all the intermolecular forces present between molecules of each substance. Okay, So here, when I do this problem, I mean, again, this isn't, you're welcome to write in a beautiful paragraph. I like to just say, like, bulleted points. Okay, BR2, IMFs, and then I would list, or just LDFs. Okay, BRCL, it's IMFs. Well, BR2 is nonpolar. BRCL, because that you have two atoms of different electronegativities, it's going to be a little polar. So it's going to have dipole-dipole forces between its molecules and LDFs. Okay. Okay, so now I've got to come to some conclusion, because when you see dipole-dipole, people are like, oh, polar is always stronger. But look at our data. It doesn't support that. Okay, so what we really need to answer here is, because bromine has a boiling point of 332, which is higher than the boiling point of BRCL. See, this would be this is how I'd wrap up my answer. Because bromine has a boiling point of 332, which is higher than the boiling point of BRCL, its bromine, try not to use the word it, BR2's London dispersion forces must be stronger than the IMFs, and again, we've already mentioned, between BRCL. Okay. Have to mention the specific forces, have to mention based on the data. Don't just say dipole-dipole is stronger. That's not true, because these are similar sizes. That bromine has a larger polarizable electron cloud. You can also add that to your answer to make it even more specific. All right, let's go to the next part of this. I know this takes a while to work through all this. We're not going to actually set this up, but I just want you to read through this. This is a continuation of that question. A 0.1 mole sample of BRCL gas is placed in a previously evacuated rigid 2-liter container at 298 Kelvin. Eventually, the system reaches equilibrium. Calculate the pressure in the container before equilibrium is established. Okay, what kind of problem does this sound like? Pressure. What else do we have? Ask for pressure is our question. We have moles, 0.1 mole. Okay. We have volume and temperature. So hopefully you were thinking PV equals nRT. And if you were, that is correct. All right, let's go to another one. And here's finally the formula sheet. I thought it was up a little bit earlier. You know, have this, you might add more formulas to yours, like we had said, percent yield. On your gas constants, remember this first one is an energy R. For our gas laws, the only two you should be using for PV equals nRT are these second two. 0.08206, because there's our pressure in atmospheres. And if you were given a pressure in torr, which is the same thing as millimeter mercury, you could have used this one. So make sure you realize for PV equals nRT, you're only going to use those. You should write that on your formula sheet so you won't accidentally use the first one. Okay, so I'm going to give you a couple minutes. I want you to go ahead and do A here. Try to write down a very specific answer. Okay, see how you're doing? Give you about 30 more seconds. Okay, so what we're looking for here is the different types of IMFs in each compound and the reason, and they told you that the boiling point of CS2 is higher than COS. So that's really, you know, why are we seeing this difference in boiling point? So, see how you did. Okay, so you should have realized that CS2, since it's linear and nonpolar, it's symmetrical, it only has LDFs. So that's what we're looking for there. And COS has two things, two types of IMFs, London dispersion forces and dipole-dipole forces. So that having those specifics gives you 1 point. Okay, so again, this is another unexpected situation. I just wanted you to see this. Lately on the exam, they've liked to give you one of these, and these are the last 2 years. So London dispersion forces in CS2 are stronger than the combination of LDFs and dipole-dipole forces in COS. And that was why the boiling point was higher. Now, because they told you the boiling point was higher, you notice they didn't mention that in their answer. If they just gave us the numbers, you need to be referring to those in your answer. But since they told us that, they didn't ask us which one has a stronger LDFs or which one has stronger IMFs. So specifically answer their question, and that will usually get you to where you need to be. Okay, try this one. Need your calculator. Okay, take a few more seconds, kind of shorten y'all from 2 minutes, but notice on this one, it says we have a liquid, but the key to knowing what to do here is that all of the CS2 has vaporized, which is telling us, what do we have? We have a gas. So because we have a gas, we can find a pressure. So here's, again, PV equals nRT on the exam a lot, but here we have to do a little bit different work this time. We're given 10 grams. We need to change that to moles. We have our volume in liters. That's what we need. We have our temperature in Kelvin, so we don't have to add 273, which is, you know, also on the formula sheet. See how you did here. The one thing I wanted to show you on this rubric, okay, you just changing grams to moles gave us a point, which is great. Solving for PV equals nRT gives us a second point. I did want to point out here, because they didn't specify what pressure units, you could have used the 62.36 and had your answer in torr, okay? Here's the problem. Calculation of pressure with appropriate units. You had to have a unit on this answer. So make sure you realize that. If you use this R, you had to have atmospheres. If you used the other version, you had to have torr. So again, that was important. What is my point here? Units are important. Make sure your answers have units on them. Okay, there's the formula sheet. Okay, here, this is another oxidation reduction. Identify the species that was reduced. Try that quickly, and we're going to get to something different. know it's past, we're right past 3. I'm going to keep going. I'm not going to do every single one of these. I will do a couple more that are different. So if you can stay a little bit longer, it might be helpful. And of course, it will be recorded. Okay, so all we're looking for here is reduction. Remember, we want to see oxidation number that goes down in value, okay, because it's gaining negatives. So the way I do this is I just start with the first substance and I see, okay, this is +1 and H plus is, the chart tells me it's oxidation number. And then I look on the other side, hydrogen's in water. I know hydrogen's not changing. That's not going to be my answer. So the next element I come to is manganese. And it's in a polyatomic ion. And I know that oxygen is going to be -2. And oxygen probably isn't going to be the answer either. But I do need to know what this manganese is, because manganese is usually something that's going to be oxidized or reduced, and you might already know the answer because this is a very common redox reaction. But notice I have a bunch of oxygens. All the oxygens together are -8. And overall, and I'm not even going to try to write that, overall the ion has a -1 charge. So that tells me that this manganese has to be +7. Okay. So that manganese has to be +7. So if I look to the other side, I can say, oh, wow, this is simple. I just have this small monatomic ion and it's +2. So I know my answer right now. I don't have to go through and assign everything oxidation numbers. My answer is the species that was reduced. Well, the species is the whole thing, okay? And again, you should say MnO4 is reduced, but specifically, that's not your final answer, okay? So I should have my permanganate. This whole thing is reduced to and it's got a negative. That whole thing is reduced to the Mn2+ ion, but what they're really looking for here is this justifying terms of oxidation number. I have to say Mn goes from +7 to +2. And if you don't have that, it doesn't matter if you pick the right thing. If you don't have these specific oxidation numbers that it changed, you would not get that credit. Okay, here's, again, this is another, I just kind of want to, let's quickly look at this. This was on last year's exam, and students didn't do very well with this, or maybe, yeah, it was last year's. Okay, so notice it says the initial and final volume readings of the solution in the burettes are shown below. Write down the initial reading and the final reading and use them to determine the volume of potassium permanganate that was added during the titration. Okay, so you got initial and then final, and it's even labeled. When we need the change, just like a change in temperature, a change in volume for something like this is final minus initial. So you had to have both numbers written down, and then you had to subtract them, final minus initial. Tell me, just look at these and tell me how many decimal places your answer has to go to based on what we did earlier. Is it 1 decimal place or 2? How are we supposed to know? All right, hopefully you're coming up with 2 decimal places. These unmarked graduations are 0.1 milliliter. And so to say how specific the volume is, we need an extra decimal place. So the answers here are, and again, yours, we're estimating here 29.55 would be final minus initial 3.35. You could have had anything, that last digit could have been, it's estimated, could have been different numbers. As long as your subtraction was correct, you would have gotten full credit there. Okay, the next one we're going to is more molarity. We've done a good many of those. I'm just kind of going to try to get to something that's a little different. So let's go to, and there's A is another oxidation number, and B is, similar calculations with molarity and getting to a gram value. I did want us to look at part C. So if you'll flip to, this is page 7, and this is part C if you had it printed at the bottom. Okay, so this question says, using the balanced equation for oxidation reduction, I can go back to that and the information in the table above, determine which reactant is a limiting reactant. I just wanted to point out that you need to review how to find limiting reactants. This problem can actually be worked without doing any math. Let me just kind of see, here are 3 reactants. This has a 1 coefficient, this has a 4, and this has a 2. So of these 3 substances, which requires the most, which is going to get used up first? Well, it's the one that's had this greatest coefficient, okay? Now, why does that work in this problem? Because all the moles we're starting with of all these reactants are exactly the same amount. You could have solved this mathematically, okay? So what I would have had to do if I wanted to solve this mathematically is to take the molarity and multiply times my volume in liters and get moles of each thing. And how I teach my students is if we take each reactant and change it to moles of the same product, and whichever product we had the least amount of would be the answer. But in this case, and I'll just slide down here, you could have known the answer just because of the, we had equal moles of every reactant. And again, as you see what they've written, the coefficients of reactants in the balanced equation, that the sodium hypochlorite would be depleted first. Okay, so you couldn't just name the limiting reactant, and you had to say why did you know? Well, it's because of the coefficients, and specifically refer to that. Okay, just make sure review limiting reactants. That definitely is going to be important. Okay, atomic structure was also in this section. And I just want to point out, here's the excerpt of the formula sheet. It's the very top of the front page of the formula sheet. These could be very simple calculations. Here we have wavelength, but this is in nanometers. Okay. Excuse me, I'm sorry. It gives you frequency. It says calculate the wavelength in nanometers. So we have these 2 formulas that deal with light. So hopefully you realize that, hey, and these are defined if you've forgotten what each symbol stands for. So lambda is our wavelength. We need to solve for that. It did ask for a specific unit. And again, now you have your own formula sheet. You could write on here that 1 nanometer, 1 meter is 1 billion nanometers, or however the equality you remember. But you would plug in your speed of light, plug in your frequency, and you'd have your wavelength, and then here's your answer. Now, again, this is the fractional version. I do it the other way and say 1 meter is 1 billion 10 to the 9th nanometers, but you'd have to have the units as nanometers. If they ask for a specific unit, you must give them that answer. Okay, I just wanted to quickly go over those. It is part of this unit. And then here's the rest of that. We've got this energy formula. It's talking about ozone and UV light breaking up ozone. So how much energy in joules does the ozone molecule absorb per photon? Anytime you solve this energy formula, it is for 1 photon only. So make a note of that. You were given frequency. Notice frequency times Planck's constant, which is also given here, gives energy. So this was a very simple calculation. All you had to do was multiply to get that answer. It's the 3rd question I really wanted us to look at. So there's the energy. Notice that's joules for 1 photon. Okay, I would even write that on my formula sheet, that is the energy for 1 single photon of light, because the context that this is usually used in is this question. And of course, there's the answer. The minimum energy needed to break an oxygen-oxygen bond in ozone is this. Notice the units, 387 kilojoules per mole. The question is, does a photon with a frequency, and this was from the previous question, have enough energy to break this bond? Okay, well, this is all about units. That is all this question's about. Our previous answer was in joules per photon. The question we're asking is about, is this light, or the bond energy is kilojoules per mole. So I can't compare joules per photon, okay, to kilojoules per mole. It's completely different units. So if I can just do a unit conversion here, and notice what's also in this section is Avogadro's number, this is when you might need to use it. So there's really two ways you can do this. You can either compare, you could take the bond energy and change it to joules per photon, or you can take joules per photon from the previous answer and change it to kilojoules per mole, which is what they have done, is they took joules per photon from the previous answer, changed it to joules per mole using Avogadro's number, and then to kilojoules. So here's the answer. So the previous frequency from the previous question, that could break a bond. You know, it has that 399 kilojoules per mole to break bonds. And as we see, that is more than what's necessary that's needed. So yes, so really you have to do the math to get this and then put that relationship together to get the second point. Okay, the next question, Unit 3, also involved gases. And I just want to make sure, especially since this exam is changing, I thought this question would be a very, would be fair game. It says the students doing experiments with CO2, the sample of a gas is at 298 and this 0.7 atmospheres. The student increases the temperature of the container to 425 Kelvin. Describe the effect of raising temperature on the motion of the particles. Okay, temperature is a measure of average kinetic energy, so you should think, okay, if it's a higher temperature, the particles have more energy, they're moving faster. So as long as you have something about more speed, higher speed, moving faster, yes, I actually would mention energy there too. I did want you to see part B. Pressure, temperature, that gas law is not specifically on your formula sheet. You could derive it from the relationship from PV equals nRT, but now you could have like the combined gas law, Boyle's law, P1 times V1. You could have all of those written down if you thought you might need one. The key to gas laws though is temperature always has to be in Kelvin. So it just said, what's the pressure in the container at this higher temperature? You had a pressure at a lower temperature. You just had to remember that relationship. It wasn't that difficult of a question, just remembering that relationship. And I'm sorry, my revealer has disappeared again. I did want to go through part C, okay? And I would highly recommend that you know both of these answers, okay? In terms of the kinetic molecular theory, briefly explain why the pressure of CO2 in the container changes as it's heated. Okay, well, you have to really know what pressure is. Pressure is due to gases colliding with the inside of the container. So if there's more energy, think about there are going to be more frequent collisions, and those collisions, since they're more energetic, will have more force. So more collisions, more frequent collisions, and more forceful collisions. Okay. We're going to go over to a couple of reactions. To me, it was important. We've looked at redox. We looked at a precipitation reaction. I wanted us to look at dissolution quickly. Write a balanced chemical equation for dissolution of this in water. Okay. This sounds like a really easy thing to write. Unfortunately, students tend to miss this, even though it's simple. Now, when you see the word dissolution, just think it's just what it sounds like, dissolving. So here's what we need to do. We have calcium hydroxide, and again, this will be mentioned later on with KSP, but this is not a reaction with water, okay? We're literally taking this solid and putting it in water. And on the AP exam, you're not expected to have to write state, so you don't even have to worry about writing the solid. If you really want to write water, you could put it over the arrows. It's not even necessary. Notice I even realized I needed equilibrium arrows. If you didn't write those, it wouldn't even matter. Here's what we're looking for. If you're told a salt, some kind of salt, ionic compound is dissolving in water, all you have to do is break it up into its ions that are balanced. Okay, this was a huge problem. A lot of students either left off a charge, had the wrong charge, or didn't balance the reaction. Another type of, and it's not really an intermolecular force since this is an ion, but a very common attraction is attraction of water to an ion. It is called an ion dipole attraction. So you're supposed to remember that the oxygen end of water is partially negative. Okay, if you're ever talking about the polarity of a water molecule, and here's its Lewis structure, instead of the space filling model that's given, the oxygen end is partially negative and the hydrogen ends are partially positive. So I was asked here to draw 4. I've placed 2 so that the partially negative end of oxygen, you could have made it touch the ion or just, you know, close to the ion. Some students actually drew the ball and stick, and that got full credit. The key was that all of these drawings you made had to all be orientated correctly. All right. And then we get to, and I wanted to go over, I've skipped page 11. That's some more IMS, which I think are very important, but I did want to talk about Beer's Law for a moment. Beer's Law has a formula on your formula sheet. It's the last formula in that same section we've been looking at today, gases, liquid solutions. What you need to know about Beer's Law is that absorbance of light and concentration of solutions are directly related. So the more concentrated a solution, and again, there's one thing I need to make sure you understand, a solution has to have a color for this to work. Okay, Beer's Law is always about a colored, notice this one's red, a solution has a color. So the higher the concentration of the solution, the more light it will absorb. Okay, now before we do a lab that deals with a spectrophotometer, you might have used a colorimeter in your lab, or maybe both. But if we have to just tell the instrument what wavelength of light will this solution absorb best. And it depends on what color it is. So the question here is, what is the optimum wavelength for this experiment? And this is what I want to set my instrument to. So again, I just want to pick what is the wavelength of maximum absorbance, and here it's about 450. So if you're within around 450 nanometers, you would have gotten credit for that. The next slide, it was a graph, and again, you're not going to have to draw a graph, so I drew it for you. This is an old question, and they were asked to actually plot the points on a graph, which, well, I think that would be nice. What I wanted to talk about here is other questions I've seen that were error analysis questions that dealt with this same topic. Okay, let's talk about what if I had a point that was above this calibration curve. Okay, so again, this shows me it's a direct relationship because the more concentrated the solution, it absorbed more, and it was in a linear, you know, it has this direct relationship. So what if I had a solution and it was way above the absorbance it should have been for that concentration? Okay, you might have seen a multiple choice question like this before. And one thing that could happen, if you've done this, we have these little square cuvettes that we put into the colorimeter or spectrophotometer, and they have ridges on one side, and the other side that's clear, we're supposed to wipe it off with a little chem wipe so that no fingerprints inhibit the light from getting through. So when you have something that has an absorbance that's too high, it could be due to the fact that it wasn't cleaned properly when it was put into the instrument. Okay, maybe there was some fingerprints that were preventing the light from getting through, so it had a higher absorbance than expected. Another situation that could happen is if I have a point that's below the line. So it doesn't have as high of an absorbance as it should have. So what could that indicate? Nothing's drawing here. That could, oops, and there it goes crazy. That could indicate that, all right, sorry, I've been on this too long. Sorry, guys. I do not want to close the program. Oh, wouldn't it close the program? I'm so sorry. All right, so did not want to close the program. Let me just kind of talk through this while it reloads. But if a point was below, had a lower absorbance than was expected at that molarity, what could have happened? And if you've done this lab, what you're supposed to do is before you fill the cuvette with the solution you're testing, you would have rinsed it with distilled water, and then you fill it with the solution you're testing, but you don't just fill it with the solution you're testing. You fill it with that solution you're testing, but then you dump it out and then you fill it again. So why would you do that? Okay, and it's because you don't want to have those water droplets when you rinsed it with distilled water. You don't want those to be present and actually dilute that very small amount of the solution. Okay, it looks like when it shut off that it did not. Let me reshare my screen. Sorry for the technical difficulties. Okay. All right, I apologize for that. Definitely operator error on that. So anyway, what I was saying is if you have an absorbance that's too low, okay, so if the absorbance was below where it was expected, it was probably due to some dilution based on water droplets remaining in the cuvette. All right, the last couple things I wanted to look at an acid-base reaction. This is an acid-base reaction, and I'll just talk you through this. Notice this is a weak acid, and you would be told it's a weak acid, okay? It's reacting with water, and it's forming ions. Notice that we're asked here to identify a conjugate acid-base pair. This is actually, for teachers, is topic 4.8. Go back and look at that. I think this actually might be eligible for the exam. I've asked that question to the College Board. No one's responded to me yet, and I will definitely get that information out to Matt if I hear that it is not. But a Bronsted-Lowry acid is a proton donor. So I would have to say that this is the acid, okay, that this is my acid. And if I'm asked for a pair, it's what it results as after it donates its proton. This is my base. And I'd have to actually connect these two. Specific, called a conjugate base, but it really just means it's a base. So this would be one example of an acid and its conjugate base, or I could have used the other pair. You had to specifically state which one you're talking about. I'm going to skip that next one. Here's another net ionic equation. I just thought it might be good for students, for you to see that you might be asked, and again, you should read everything. I'm just kind of skipping to the highlights here. This says AQ. So this is a salt. I know it looks really strange, but you're still expected to know to split that into ions. And you really should know, because this is still eligible, that HCl is a strong acid. So make sure you review those 6 strong acids. This is in Unit 4. Strong acids or strong electrolytes, they completely ionize in the solution. So if you break up the K+ and the rest of this whole thing is a negative ion, and then your H plus and your Cl minus will be broken up, you're going to end up with 2 spectator ions. So let me show you that. Oh, I was just going to write that. Okay, that was the math part of it. So your final answer here, and it's not letting me write it, is you're going to have this negative ion plus your H plus gives you, it's going to make this weak acid. This formula is right here. And I apologize again for the technical difficulties. This is hypochlorous acid and water. You would be told this is a weak acid, or you should even know it's a weak acid since you know the 6 strong acids. So weak acids stay their whole molecule plus water, do not break up any acid. So this would be the reaction I would write. I would write plus water. They also accepted the reaction without the water. There is a few more. The last free response I would highly recommend that students that you try is the KI. This would have been on your mock exam. I highly recommend you work on this. The teachers will have the answers to all of these. And let me see what time it is.